Hello, everybody. Today, today we're gonna talk about retirement savings. This is a much more applied, maybe, or more of a specific example of the compound interest that we've been talking about, with a little twist. So, I hope that you all learn a lot about when and how you should start your retirement savings and why it's important, or why people say that you should start early. Uh, yes, I learned a lot preparing this lecture, so hopefully you do as well. So, today, section 10.4, retirement savings. Oops. All right. So, we will use our new knowledge about compound interest to investigate your future as a retired person. All right. So, quick statistic first, I guess. The National Institute for Retirement Security, so here's a remark. They published a study that in 2015, the median retirement balance amongst all working American households was $3,000, which is not very much. So, according to the NIRS, in 2015, the average American working household had 3,000 saved for retirement. That's not very much. And 45% had no retirement savings. So this should strike you as precarious, and I hope that that this section will convince you to, even if you don't have a well-paying job. I mean, I know you're all students. We're all in the same situation, but as soon as you have a little bit of income to start putting aside, it really could help to put away $20 a month, even just like really small amounts. They will add up, as we will see. Good. So the fundamental question for retirement funds, what happens when you set aside a fixed sum regularly, like every year or every month, you set aside a fixed amount of money and let it compound interest for a long time? You regularly, i.e., every year slash month, put aside a sum of money and let it compound interest. And so this is the big difference here between compound interest and retirement funds, is that with the compound interest you make one investment and you calculate how much interest is compounded every time. But now we've got one more bit, which is that you don't just make an initial investment and let it compound interest. You continually make more investments. So the difference between this and compound interest is that instead of putting in one sum, a principal, and letting it accrue interest, now we put in multiple sums spread out over some amount of time. Okay, so that's really all it comes down to, I think, is this question. So retirement is just kind of the general setting, but the fundamental mathematical question that we're asking now is what happens when you regularly put aside a sum of money and let it compound interest, rather than just putting in one sum of money and letting it compound interest. And we're going to investigate two examples. We will investigate two examples. The first one is going to be the instance where you set aside $1,000 per year for 44 years with an annual return of 6%. So this is kind of like our example of a long-term, like you put money into your retirement fund over a longer period of time, but you put a smaller amount of money in. $1,000 per year might seem like a good bit, but I think it's pretty average. That comes out to $86 a month or so, $83.33 per month. So yes, that'll be our first example, and our second example is going to be setting aside $2,000 per year, so twice as much, but for half the amount of time, 22 years, at the same APR. So one, you set aside $1,000 per year for 44 years at a 6% annual return. Great. Or two, you set aside $2,000 per year for 22 years. Annual return. Okay. And well, let's just jump right into it. So this so this first example, 44 years. That's like saying that you maybe start your fund at 21 years old and retire at 65. That's a pretty average way of thinking about it. I mean, I started mine a year ago or so. So I was a few years older than 21, but I think I was still convinced that it was a good idea to start early. But this is also a strategy. This second one, example 2, is also a strategy where maybe you don't have money to put in right away when you're young and a student and in debt. Maybe your first priorities are paying off your debt, and then you think, okay, well, maybe by the time I'm 40, I'll have a job that's well-paying and I can start putting aside money. So we are going to investigate those two cases. Good. So let's do example 1 first. Start a new page. Example 1. So, at 21, you decide to start putting 1,000 per year. That's about $83.33 per month into a retirement fund with a 6% annual return. How much will you have at 65 years old? i.e., after 44 years. Okay. So, how might we start calculating this? I guess that we'll use similar logic that we were doing to the compound interest, right? So we're going to break this down into kind of, instead of thinking about 44 years all at the same time and what kind of a formula we might need, the good mathematical intuition is to break big problems into smaller problems. So I'll write that. The mathematical intuition break big problems down into smaller ones. Okay, and here's how we're going to break this down. There are actually a couple of different ways that we could break this down. My initial intuition was different than the book's, but I'll keep things consistent. So here's how we're going to break it down. So the very first thing you do, right, is say at the end of year one, you put $1,000 in. And if that retirement fund gives a 6% annual return, I'll make a note so that everybody's clear. This is compounded annually. So that's compound interest, right? Which means, well, we had a formula for it, but why don't I go back and just do it out? So, solution. So, first step. At the end of year one, you put in $1,000, right? So let's just think about that first $1,000. If we want to, here. So at the end of year two, that $1,000, so you receive I before E except after C. 6% on $1,000. So that's equal to, how do we calculate 6% of 1,000? Multiply it by 0.06, and we add that on to the original amount. So remember that if you want to figure out how much you made, how much money you have after you get 6% of $1,000, now you have 1.06 times $1,000, which is $1,060. Good. 6% of 1,000 is 60. Add 60 onto 1,000 to get $1,060. So, and you deposit another $1,000. So total, so year two end total is 1,000 plus 1,060, which is 2,060. Okay. So that's step 2. Why don't I write that here? Year 2. 3. End of year 3. How much will we have? Well, we will have made 6%. Made 6% of 2060. So now we have 1.06 times 2060, which is whatever that is. And we'll get add 123.60 to 2060, and we get 2,183.60. Now, I want to show you an alternate strategy for calculating that. Notice this is also 1.06, so that's the 6% interest on the first $1,000 accumulated 2 times, right? So on this thing, 1.06 times 1.06 times 1,000. Maybe the parentheses are making things more confusing. I can delete a couple of them. 1.06 times 1,000. So that's the interest, and so this is like the interest that you've accrued 2 times on the first $1,000. 2 times accrued interest accrued 2 times on first $1,000. And then we can add to that the interest that's accrued 1 time on the second $1,000 plus 1.06 times $1,000. This is interest accrued 1 time on second $1,000. And we should get a total of... Oh, we should add also the $1,000 that you're going to put in at the end of year 3, right? But when we multiply this out, we're going to get 1.06 squared times 1,000. So let's go find the calculator. Okay, so here we're going to have 1.06 squared times 1,000, so we move the decimal point over 3 places. We get 1,123.60 is 1,123.60. And then we'll add to that, we'll add to that 1.06 times 1,000, which we calculated up here, 1,060. And what we'll get, I don't know why I wrote that all the way down there, I might as well have just wrote it here. I also don't want to confuse you. Okay. And so in total, what do we get? This is 2,183.60. And so look, these are exactly the same, right? 2 different methods. The first method was my initial thought. The second method is the book's initial thought. But I And we're going to use the books method, but I still want to show you that there's always two ways of answering a problem, really, often. Or maybe always, and we just haven't always found it. Good. So, now, so that means, so plus the $1,000 deposited at end of year 3 is equal to, so now we have 3,183.60 at the end of year 3. Okay, so now let's put together this pattern. So the pattern. End of year 1, end of year 2, end of year 3. The total is going to be, so the total after year 1 was just the $1,000 we put in. The total after this is going to be 1.06 times $1,000, right? That's what we just calculated. Now the total after year 3 was what we were just doing a second ago. This is now 1.06 squared, right? That's the same thing as 1.06 times 1.06 times $1,000 plus 1.06. Oh, we were supposed to add the $1,000 deposited at the end. So in total, at the end of year 2, we didn't just have 1,060. We had 1,000 plus 1,060 because we deposited again. Right. So plus 1.06 times $1,000, the 6% you make on the second, the 1,000 you put on in at the end of the second year, plus the $1,000 that you put in at the end of the third year. And so, if we go all the way down, now that means that at end of year 44, how much are you going to have? Well, it looks like we have a pattern. At the end of year 3, we had 1.06 to the 2, which is 1 less than 3, right? Times 1,000, because remember, we didn't accumulate any interest on the end of the first year. We put in the money at the end of the first year. This is why it's raised to the second power instead of raised to the third power. And why we just get the 1.06 raised to the first power. We've only accumulated interest one time at the end of year 2. Which means that at the end of year 44, we will have accumulated interest 43 times on the first 1,000. We have accumulated interest 43 times on the first 1,000, 42 times on the second 1,000, and 41 times on the third, etc., until we get down to finally we will have accumulated interest 0 times on the 44th $1,000. So this kind of makes sense because, I mean, it's kind of pointless to put in $1,000 at the end of your 44th year when you're only doing it for 44 years. So basically you're putting in $1,000 and instantly taking it out so you don't accumulate any interest on it. But so what does this equal? So then the total then the total t after 44 years, actually we're going to call your total v. V total after 44 years is going to be 1.06 to the 43rd power times 1,000 plus 1.06 to the 42nd power times 1,000 plus on and on forever down to plus 1.06 times 1,000 plus $1,000. Okay. So, that looks like a really long and complicated formula. And however, will we figure out what this is? However, how shall we ever know what this is? Well, the reason I'm saying it like this is that we don't need a calculator. I have a fun trick. This is an application of a mathematical concept called geometric sums or geometric series. In reference to the infinite version of this. I guess these are geometric sums. And the idea of geometric sums is that you always have these exponents which get smaller and smaller and smaller. And so here's a trick. So this is a cool trick because it also works for many other cool examples, and I think I'm going to make another little video after this one just talking about geometric sums and series for a little bit because they're really fun. Okay, so here's how we're going to write it out. Let's write our sum b as b, here I'm going to leave a little bit of space, b equal to, I'm going to factor out, I'm actually going to write it in the opposite order, right? So I'm going to start with the 1,000, and then I'm going to get bigger and bigger and bigger and bigger on the powers of 1.06. And I'm going to factor out a 1,000. Maybe I won't. V is going to be 1,000, plus 1.06 times 1,000. I'm going to zoom in because this is going to get big. Plus 1.06 squared times 1,000 plus forever plus 1.06 to the 43rd times 1,000. Okay, and above this, I'm going to write 1,000V. Actually, no, sorry. I want to do 1.06V. Okay? So what I mean by this is I'm going to multiply everything in V by 1.06. And I'm going to distribute it through. So basically I'm taking this whole thing and I'm multiplying it by 1.6, right? But instead, I'm going to distribute the whole thing through. So this is going to become 1.06 times that, plus 1.06 times that, plus 1.06 times that, etc. So this is going to become, and I'm just going to space it out a little bit more. This is going to become 1.06 times your first 1,000 here, times 1,000. So this is coming from 1.06 times this 1,000, and you're getting 1.06 times 1,000. Okay? And then, if we multiply our 1.06 by 1.06 times 1000, we'll get 1.06 squared times 1000. Maybe I should keep it consistent with the little dots instead of x's. Times 1000. And you can tell that this is going to keep on going on forever. We do 1.06 times 1000 times 1.6 times 1000 times 1.06 squared times 1000. So this one is going to give us 1.06 cubed times 1000, which is going to go there. But I'm going to write dot 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 and see what happens when we get to the end. So when we multiply 1.06 times the term that came right before this one was 1.06 to the 42nd. Multiply that by 1.06 and we'll get 1.06 to the 43rd. So what we'll get at the end here is 1.06 to the 43rd times 1000 plus 1.06 times this last term, which is going to become 1.06 to the 44 times 1000. That's an important term. Because now what we're going to do is this. This is the tricky part. We're going to subtract one from the other. Maybe I'll do this in a different color so that you see what happens. I'm going to subtract the bottom one from the top. Just like a whole, because this is just one equation and this is another equation, and you can just subtract one equation from the other. So what we're going to get here is 1.06v minus v, minus 1v. So that's going to give us 0.06v on this side. And what are we going to get on the right-hand side of our equation? Well, now we're going to get, look at this 1.06 times 1000 on the top, and the 1.06 subtracted 1.06 times 1000. These are going to cancel out. All right? And same here. This 1.06 squared times 1000 is going to cancel with the 1.06 squared times 1000. Everything in the middle is going to cancel. This last one, 1.0643 times 1000, is going to cancel here. And then what we're going to be left with is just this term and this term. Those are the only things that are left. And so what we're going to get is that 0.06v is equal to negative 1000, because now we're subtracting this first 1000, plus this term over here, which never changed, 1.06 to the 44 times 1000. So plus 1.06 to the 44 times 1000. This is quite cool. So what we're going to do is we're going to rewrite this. We can factor out 1000 on this side. So that's 0.06v. I'm going to stop using red again because I don't like it. Is 1000 times 1.06 to the 44 minus 1. I just flipped these two terms around and then factored out a 100 from them. And now if I divide both sides by 0.06, divide both sides by 0.06, and what I get is that v is equal to 1000 times, 1000 times 1.06 to the 44 minus 1 divided by 0.06. Okay, and so that is how you calculate retirement savings. Now we can just enter this number into a calculator. Enter this into a calculator, and what do you get? Well, why don't we do it? So 1.06, and now we're raising this to the 44th power. Okay, and that's 12.985. Now we're going to subtract 1. Okay, That gives us 11.985. And now we're going to divide that number by 0.06. Why don't I say equals so that I don't screw anything up? Remember that sometimes basic calculators can screw up order of operations. So now I'm going to divide all of that by 0.06. Okay, and I'm going to get 199. And then I'm going to multiply all of that by $1,000. That's the amount that you were putting in every month. And what we're going to get is $199,758. $199,758. And how many cents? 3 cents. Why not? We'll include it. So, if you remember what was going on from the beginning of the example, you started at age 21, so you put away $1,000 a year at a 6% return for 44 years. And at the end, only putting $1,000 away for 44 years. So that means in total, you put $44,000 into your account. And what you came out with was $199,000. That's nearly $200,000. So why don't I just clarify? This is $199,000 in the fund at age 65 after 44 years. And so the remark I want to make is that, well, I just made it out loud. The remark I want to make is that you only deposited $44,000, $1,000 per year. But you came away with nearly 200,000. That's a lot. That's more than 4 times. You more than got 4 times the amount that you had in there before. So, good deal. Okay. So now I want to well, why don't I give a formula, which is basically what we just calculated. This procedure gives a formula for calculating annual retirement savings. So, and this formula is V, which is going to be your total savings, it's going to be equal to, so what was it that we did up here? This ended up being the amount that you put in per month times, and then in parentheses here we have your interest rate, 1 plus the interest rate, raised to the power of the number of years that you had it, that you were doing it for, minus 1. All of that over the interest rate, 0.06. So this is going to be, what are the letters? Why don't we say P? This is your yearly contribution times 1 plus R, where R is your interest annual annual being important, remember it can change when it's monthly. Annual interest rate raised to the number of years minus 1, all of that over r. Okay, so this is a good formula. And why don't I put a little thing around it to impress that upon you. I don't like that thing, but I can resize it. I can make it bigger. Good. This is your annual retirement savings. That's kind of an ugly thing. Nah, forget it. Alright. So, now that we have your annual retirement savings formula, we can move on and do the second example in a much shorter amount of time. So, sorry, I'm just trying to get these things all nice and aligned. Okay, and then I do still want to put a little box around it because I think that this is a important formula. Oops. Why is it not filling it in? Delete it. Delete it. Okay, forget about it. There's your annual retirement savings formula. Good. So let's move on to example 2. Okay, so remember example 2, I'll copy it from up here. Example 2, you set aside $2,000 per year for 22 years at 6% annual return. The same as the first one. So let's say that in this situation, so say now you didn't have savings to contribute until you were 40, so 22 years, retiring at 65. That means you started at 43 years old. Can you catch up? Okay. Well, without going through all of that long process that we did for the last one, we can just go back and use our formula, right? So if our formula is V equal to P times 1 plus R to the number of years. Oops. Let's go back. Don't mess with me here. Paste. So now, why don't I color that a different color? Because colors are fun. Good. Because now I can't see that color. Good. So, alright. And so now what we want to figure out is, so now P is twice 1,000, so P is 2,000. R is still 0.06, the 6% AP annual percentage rate, APR. Y, the number of years, is now 22. So what do we get? We get V equal to 2,000 times 1.06, that's 1 plus R, raised to the power of 22, minus 1, divided by 0.06. And what are we going to get? Why don't we go to our handy dandy calculator? 1.06 raised to the 22 minus 1 is equal to that. We're going to divide it by 0.06. to get 43.39. And then we're going to multiply that by $2,000 that you were putting in every month. And we're going to get 86,784 and 56 cents. Sorry, 86,784.58. So even though you now contributed twice as much for half the amount of time, this is less than half of what you would have saved if you started young. So I guess this really is the moral of this section, is start saving young. I don't think it's such a bad moral. We should maybe just be doing math in math class, but I don't know. This is applications of math, so we do things like this. Okay. Now, I want you to, just a remark, even if you had been, in fact, even if you put away 4,000 per month, per year, for 22 years. V is 4,000 times 1.06 to the 22 minus 1 over 0.06 is only going to be 2 times this other one, right? This is just 2 times 2,000 times the other one. So that should just be 160, 73, 569.16. So you're still not even there. So start saving young. That's the moral. Remark. Notice that when I changed the amount that you put in every year from 2,000 to 4,000, but from 2,000 to 4,000, but this whole bit stayed the same, right? We exactly doubled the amount of money. But when the exponent here changed from 44 to 22, we did a very different thing than doubling. It went a lot more than double. So, remark. There is a linear or proportional relationship between V and P, but an exponential relationship between V and Y, the number of years. And so I guess maybe nobody is, I don't know how many of you actually have thought about what it means when you say exponential. I know in the math community people are actually a little hesitant about saying that something grows exponentially unless you know that it has to do with an exponent. But in this case we can say quite literally that there's an exponent, that it makes an exponential difference to start saving early because the number of years is actually in this exponent. So on a very deep level, this is an exponential relationship, and it is exponentially better to start saving early. Terrific. Good. So for this, I wanted to just show you a little bit from the book here. Yes, this table. This is a table which compares how many years that if you save for 10 years under our same conditions, putting in 10,000 annual savings with a 6% APR. And we can look at how this exponential curve, this dotted red line, goes up quite steeply as the number of years increases linearly. Notice that the years are increasing by 5s every time. 10, 15, 20, 25, 30, 35, 40, 45, 50. But the values that you make after that number of years spike very quickly. So after 10 years, you only make 13,000. 15 years, you make almost twice as much, 23,000. After 40 years, you're at 154,000. And after 50 years, if you can save for that long, you almost double it again. Between 40 and 50 years, you almost double the amount of money you have saved, from 154 to 290,000. So, good. That's all. You can take a look at that page in your textbook. I'm going to keep on moving so that these videos don't keep being so long. Yes, I wanted to do a monthly example. Now, an example where money is put monthly into a retirement fund. Say, by an employer. Taking a sum out of your monthly pay and putting it in a tax deferred 401k. So, in case you don't know about these things yet, I guess we've been oversimplifying things a little bit here, saying that we're giving money every year and we're compounding it every year. In fact, most people put money into a retirement savings via 401k or something similar that many employers will give you the option of taking out a sum of money from every paycheck and putting it directly into a retirement savings fund. And really the calculations for figuring that out are very similar to the calculations we were doing for the yearly contributions, just adjusted a little bit so that the interest rate is no longer yearly, but now look at the monthly interest rate and how many times you put in monthly. But it's really the same kind of thing. And we specify tax deferred because this means that it's not being taxed you're not paying taxes on the money you've put into your retirement fund until you take it out at the very end. So for now, we can do all of our calculations without worrying about taxes. Okay, so we're going to use many of the same numbers. We will use the same numbers. So our interest rate is 0.06 annually. So this means that monthly R over 12. So that's the interest. If you get 6% interest per year, then you've got a 12th of that, which is 0.06 over 12, which is 0.005. So this is now your monthly. I'll put this monthly interest rate. Okay, so divide the annual interest rate by 12 to find your monthly interest rate, and also P equals 1,000 annually. This means monthly contributions of 1,000 over 12 is approximately $83.33. Okay? And we can really do a very similar thing. We can treat these months just like they were years, and the monthly interest rate just like it was the yearly interest rate, and we really do the exact same process to compound it. So now we just have to figure out, so now 44, and finally, so we had these three calculations. We have to figure out the monthly interest rate, the monthly contribution, and not only, so now, before it was being compounded 44 times, once every year, but now it's getting compounded 12 times a year, and so what we need is 12 times 44 is, what is it? I did this out. 528 monthly contributions. So then your total V is going to be the amount that you're contributing monthly. That's 83.33 times 1 plus your monthly interest rate of 0.05, 1.005, raised to the power of the number of times. Remember, the reason we were raising it to the number of years here, 22, was because that was the number of times it's compounded. And so here, it's actually getting raised to the 528. This is the number of times compounded. Okay. Minus 1. All of that over our new monthly interest rate, 0.005. And what will this give us? Well, this will give us, why don't we go out and do this? 1.005 times, oops, not times, raised to the power, 528, right? Yep. Minus 1, 12.921, blah, blah, blah. And then we're going to divide that by 0.005 to get 2,584. And finally, we multiply that by the amount that we were putting in per month. So we multiply that by 83.33, and we get a total of 215,346. 215,346 and 82 cents. So actually, this is interesting. Using the same contribution, you still contribute 1,000 for 44 years. That's $4,400. You still contribute $4,400. But just the difference that you were contributing it monthly, and that you were getting paid, the interest was being compounded monthly, brought this up from about 200,000 to 215,000. This isn't nearly as big of a jump as the jump from 85,000 to 200,000 when we were saving for twice as long, but it's a jump nonetheless. So this is kind of interesting. Remark: same amount invested, same interest rate, compounded more often, made you about 15,000 more. That's kind of interesting. So, good. All of these are things to ponder. I'm not trying to tell you that they're like, I'm just trying to show you how to do these calculations, really. Yeah. So, one thing to note, this is simplified. So I was actually having a conversation with my roommate this morning where he was like, all right, if you're doing all of these calculations, why don't you figure out how much interest I've been making? If I now have this much money and I put I started my retirement savings 7 months ago, started putting in 114 per month, which was like, I don't know, 4% of each of his paychecks. And he was saying, okay, so then what's my interest rate? And we went through and we figured it out. And it came to something like 3%. And I was like, wow, a 3% interest rate is really low. I mean, like most 401ks have an interest rate between 5 and 8%. So 6 on average is pretty good. But then we were thinking that actually many 401ks will invest your money in the stock market again. And so this interest rate isn't necessarily going to be a constant amount. The interest and if it fluctuates like our economy is fluctuating at the moment, it could drop pretty quickly, and the fact that he's only had money saved for 7 months then means that you see quite a big difference in the average interest rate. I'm sure over 44 years that average interest rate levels out to something more reasonable, but that's kind of interesting. The interest rate is not typically fixed at 6%, but depends on the economy / your plan. So 6% but 6% is not a bad stable average. So I'll just put that out there, that maybe you should calculate your own, but be careful of doing calculations based on a small window of time in which the economy is fluctuating quite a lot. The other way that it's simplified, the other way we've simplified this is by assuming you contribute a consistent amount every period. Generally, people make more as they get older, and contribute a higher percentage or a higher amount. Okay, so let's do one more example. For 10 years, you contribute 150 per month. So let's do the same. So same R equals 0.06. So because this is again monthly, R over 12 equals 0.005. And we're going to change the contributions, but the number of years and Y number years 44. So that's going to be 512 months. Okay. So for 10 years, you're going to contribute 150 per month. And then you think after 10 years, you'll have gotten a raise. So For the next 10 years, contribute $225 per month. And then next 10 years, contribute $350 per month. And finally, you get older and you make more money. It's all good. So the last 14 years, contribute $500 per month. Now, how are we going to calculate this one? Well, I suggest that we break it down into a similar strategy that we were using for the first example. That is, let's calculate how much money you make off of your $150 per month for the whole 44 years. And then we'll see how much money we can add on to that for the extra money you've been contributing for 34 years. And then you will have been contributing a little bit more than that for 24 years, and finally a little bit more for the last 14 years. So, to calculate total savings, try calculate A, savings on $150 per month for 44 years. That's 528 months, remember? And then B, we're going to calculate the savings on the $75 extra that you start contributing. So that's the $75 per month for 34 years. And 34 years is, I did this out. So here, let me see. That's 408 months. C, savings on how much did you add after the 20-year thing. So then going from 225 per month to 350 per month is 125 difference. So then 125 per month for 24 years, which is 288 months. D, gonna have your savings on the extra going from 350 to 500, extra 150 per month for 14 years. And 14 times 12 is 168 months. Okay. And so once we add all of these things, adding all of this together gives total savings. Right? Because really, there's no difference between this and doing your 150 a month for 10 years plus 225 per month per 34 years. These are really the same calculation done two different ways, but this way is just a little bit simpler in my opinion. So remember, the 75 here came from the difference 225 minus 150. The 125 here came from the difference between 350 that you contribute for the third period minus the 225 that you were already contributing before. So that's 125, etc. Okay, so calculating this, we'll get V equal to, well, what was our formula? We do the total number of months. V is M, number of months, So, why don't I say? This is the monthly saving formula. Okay, and that's the total amount is going to be the number of months times 1 plus r over 12 raised to the t, where t is the number of months that you're saving for, minus 1 over r over 12. And this is really just the same thing as the annual formula, but with r replaced by r over 12, your monthly interest rate, and y replaced with t, this is the number of months, where, sorry, I shouldn't say that, where m is your monthly contribution, r over 12 is your monthly interest rate, and t is the number of months. Okay? So now in our example, we get V is start off giving 150 per month times 1.005. Remember, this is 1 plus r over 12. R over 12 was 0.6 divided by 12, which is 0.005. Okay? Raised to the number of months. Remember, this first one, this is where we're working on part A here, is 528 months. So remember, this one's A. 528 minus 1 over 0.005. Okay, and then we'll add to that your 75 extra dollars that you were contributing at the same interest rate for only 408 months minus 1 over 0.005. We're going to add to this the extra 125 that you started contributing for the last 24 years, which is 1.005 times 24 times 12 is 288 minus 1 over 0.005. And finally, we're going to add to that plus 150 extra that you contributed for just the last 14 years. 168 months minus 1 over 0.005. And because I've already plugged these into my calculator, I won't do them again for you because it takes time. But I'll just say that this comes out to $606,899.21. That's a lot of money. You could be rich as an old person there. So do that. Do that. So the moral of the story, do this and you'll have savings when you're older. I mean, it's pretty simple. The reason I'm doing all of this is so that you can do the calculations. And if you're like me, people say things like that and you don't really know how much they mean. It's like, yeah, well, obviously I'll be better off if I start early. Thanks for telling me that I should start my retirement fund early. I didn't know that if I put more money in for a longer amount of time, that I'll have more money in the end. But the interesting thing is this exponential business. The whole crux of this section is that your retirement savings grows exponentially based on the number of years that you have it in there for. Not at all relevant the amount of money that you're putting in general. So, I mean, it is relevant, but it's proportional. The amount of money you put in and get out varies proportionally. the number of years you leave it in for gives you an exponential amount more money. Okay, and I'll make another quick video on geometric sums, but that's not related to this financial math business. It's just fun stuff. So, bye.